let's see, there's maybe, I guess everybody's here. Okay, so this lecture we get the story on surfaces. And what's going on here, well, first of all, let's plug this in. Okay, so if we go back to our old friend here, the organization chart, we're now going to talk about this corner up here where it says sea state and bottom reflectance, and that's basically the boundary conditions that we need to solve the radiative transfer equation to get all of the good stuff. And so surfaces occur in our work here several places. First of all, the sea surface reflects and transmits light. If it's a shallow water, then you've got a bottom with some kind of sand or seagrass or whatever on it that reflects surfaces. And of course, if there's an object in the water, then that surface of that object will reflect light and affect the visibility and so on. So anyway, we'll just see what's going on up there today. And we'll talk about this thing called the bidirectional reflectance distribution function, the BRDF. And really what that is, it's the general way you describe how a surface reflects light. We've talked in here about Lambertian surfaces. We'll figure out what those are. We'll talk a little bit about level air-water surfaces and this thing called the n-squared law for radiance, and a little bit about how people model wind-blown sea surfaces and how it's done in hydrolite and how other techniques work, but no great detail on this business down here. Okay, so the BRDF. So you remember we've got these fundamental IOPs, which are the absorption coefficient and the volume scattering function. And the volume scattering function says, well, if light's going along in this direction, or radiance, and it interacts with a particle, then here's the direction it can go off in some other direction. So basically, the IOP is the volume scattering function is the IOP that tells you how a volume of light scatters, or volume of water scatters light. And the BRDF is basically the same thing as the VSF, it's just for surfaces. So the BRDF will tell you if I've got light coming in some direction or radiance in some direction, it hits this surface, how does it reflect off into other directions? So just like the VSF, which is from an incident angle to a final angle, and it's a function of wavelength, and usually we just write the difference in the incident and final directions as a scattering angle psi. And likewise, the BRDF is from an incident direction to a final direction, and in general it will be a function of wavelength because the surfaces are colored in some way or another. Okay, so the geometry for how the BRDF is defined is this. So we've got some surface here which is kind of colored in green. We're going to have incident radiance coming from some direction, theta I and phi I in some coordinate system here. And so that radiance is going to come in, hit the surface. It's going to be reflected off into some other direction and some amount of radiance into some solid angle over here. And so we've got these two incident and reflected angles, and usually it's only the difference between the incident and final azimuthal directions that matters, although in a more general case you can have it depending on the exact directions and not just their difference. But anyway, this is sort of the basic idea of the geometry. And then how the thing is actually defined, and if you look, this goes all the way back to documents at the National Institute of Standards and Technology, NIST, and they have people there who do nothing their whole lives except worry about how surfaces reflect light. And the way it's defined is you say, okay, in this incident radiance here, that actually kind of corresponds to a little bit of incident irradiance, because I've got radiance into some solid angle And then if I wanted to get the plane irradiance onto this surface, well, remember, what's ED? It's the integral of L times cosine theta times d omega. So, and then you normally think of, well, I'm going to integrate over all directions. But if I just pick a little element of direction here, then this incident radiance, we take that times the cosine of the incident angle times the little element of solid angle that corresponds to this radiance here. Well, that's really a little element of plane irradiance onto the surface. The cosine is converting this direction into something on a level surface. So we have this little bit of incident irradiance, and that's going to give us some little bit of reflected radiance going into some other solid angle here. So the way this thing is defined is simply, for this element of incident irradiance, we get a little bit of reflected, an element of reflected radiance. Now that's the mathematical definition. The operational definition, what do you do there? Well, you set up a light source. If you're measuring it in the lab, you put in a collimated beam of irradiance where all the light's coming from just one direction, not from the whole hemisphere. So you measure the incident plane irradiance ED onto the surface for some incident direction, and you see how the surface reflects light into all other directions. And so that's the definition as Ken Voss would measure it, and this is what I would play around with in my equations. So notice it has units of per steradian, just like RRS does, but more on that in a minute. Now,
downwelling irritants, what you said, it's not the whole hemisphere?
Right, see, we're only taking light from one particular direction. So that's being converted into how much plane irradiance do I get here, but just from light coming in one direction. Now, when we go out in the ocean and we measure ED, we've got light coming from all directions. So this would be just basically like the sun is in a black sky, I get an ED. Okay, so that's the idea. So this thing depends on what's that incident direction that's creating the ED, and then what's the reflected direction that's describing the L here. Now, the reason the mathematicians like this is if you ask me, how much light is being reflected from this surface? Well, I take this equation here and I'll say, okay, well, there it is again. I just want to know the total light coming up when I look at the floor here. Now I take the incident radiance from a given direction times the BRDF, converts it into a reflected direction, and then I integrate over all incident directions. So now the light I see reflected from the floor, some of that's coming from this direction being reflected, some's coming from that direction being reflected, and so on. So I just want to sum up I'm integrating over 2 pi all incident directions here, and then for each of those incident directions, the BRDF converts how much of that is reflected into the final direction that I'm interested in here, and I integrate over the whole thing. So that's how the BRDF gets used by the radiative transfer people. And if you look in hydrolite, you'll see an equation that looks like this, and there's a thing called the radiance reflectance function, which is just the BRDF times the cosine. If I wrote the book again, I would do it all just in terms of the BRDF, because that's what people usually talk about. Okay, so the BRDF here, as I just said, it's has units of per steradian, and it looks a lot like the remote sensing reflectance, which is once again a radiance divided by an ED incident irradiance. But the difference is here in RRS, you're taking ED from all downward directions and looking at how much is reflected into one direction. Here, you're taking one incident direction and how much is reflected into a particular direction. So they have the same units, but they're not quite the same thing. And if you actually want to compute the BRDF in hydrolite, and maybe that's the next one, yeah. What you do is you run hydrolite, you pick the idealized sky model. You put the sun at the zenith and the rest of the sky is black. And you get that collimated incident irradiance down, see what directions that goes off to. And let's say you're looking at the BRDF of the whole ocean. So the sun at the zenith and the black sky will give you light reflected off in all directions. And you record that information, then move the sun over to 10 degrees, still in the black sky, do the hydrolite simulation, look where all that light goes, and on down to where you put the sun, and right next to the equator at say 85 degrees, that gives you a collimated incident irradiance. You get reflectance in all directions, and then you take all of that information, well, you now have all incident directions and all reflected directions, and screw all the pieces together, and you then get the BRDF of the ocean. So that's how that's done in hydrolite. And I have, a special version of hydrolite that simply loops over all sun angles in a black sky and writes out a big file that's then the BRDF of the ocean for that wind speed, those IOPs, etc. Okay, now, so here's just a couple of examples of that. So here's a run here, wind was 6 meters per second, case 1 water, infinitely deep, blah, blah, blah. Well, if I do these runs and I look at the total upwelling radiance above the sea surface, and I use that as my reflected radiance to divide by the incident irradiances and get a BRDF, and what does that look like? Well, here's one here. These are viewing angle in theta and viewing angle in phi, and then the sun was right here. So if the sun's at 40 degrees and it's in the phi equals 0 direction, well, that light's going to come down, hit the ocean, and be reflected off. So if you look, here's the BRDF computed with the total upwelling radiance. Now you get this big bump out here. Well, that's the surface glint. So all you're looking at in this figure here is for one particular sun position, you're seeing, looking off in these directions, you don't see much, but then if you look in the direction where you're seeing the sun glint, now you get this really bright glitter pattern. That's what's shown there. If I computed a BRDF for the water leaving radiance just using LW, then here it is, much different vertical scale. So this is up to 0.14 per steradian. This is 0.004. So you can see, you don't see a glitter pattern here. You just see, here's where the sun was, and here's the specular direction over here. And it's not level though. Notice it, if it were what's called a Lambertian surface, this surface here would have the same value for all directions. Well, you don't quite see that. There is a little bit of structure to it. In the old papers, when people did pencil and paper calculations, they would often assume that the water leaving radiance was isotropic, or that the surface was Lambertian. Well, that's, to a first approximation, okay, but the water leaving radiance really does depend on viewing direction, and that's what this BRDF correction for the normalized water leaving radiance is all about, is correcting for these little effects here. Okay, enough said on that. It's just that keep in mind that the real water leaving radiance is not really a Lambertian. It's not really Lambertian. Okay, so this business of Lambertian BRDFs. So you'll see statements where people will say something like, a Lambertian surface reflects light equally into all directions. Lambertian surfaces are therefore also called isotropic or uniform or perfectly diffuse reflectors. And then you go read the next paper, and it'll say a Lambertian surface reflects light with a cosine angular distribution. Lambertian surfaces are therefore called cosine reflectors. Well, here's my two mental images of this. In one case, it says they reflect the radiance the same in all directions. So it must look like this. And the other one says, no, it reflects light in this cosine pattern. So here's measured to the normal, here's the cosine of the angle here. So it would be some kind of reflectance like that. So which of those is correct? Well, if you think about it and you actually really read carefully, if they're saying things properly, what it is that a Lambertian surface reflects radiance the same in all directions, but it reflects intensity from each point in a cosine direction. So what's happening here, remember, intensity is power per unit solid angle. So each point of the surface, when light comes in, the red arrow reflects off, each point is reflecting in this cosine pattern. Now, if I want to measure the radiance reflected by the surface, I'm going to have a radiometer, I'm going to look at the surface, it has some finite solid angle that it's looking at. And so it's summing up this cosine pattern from a whole lot of points in its little footprint on the surface. And the size of this little footprint depends on 1 over the cosine of this angle. If I'm looking straight down, I see a small patch of surface. If I look out here with the same radiometer, I'm seeing a bigger piece of surface. So each point is proportional to the cosine for the reflected light, but as I move my radiometer, I see more and more points in proportional to 1 over cosine theta. So the cosine pattern here and the 1 over cosine here cancel out. And the radiance I measure is then independent of the viewing direction. Does that make sense? It's a little weird deal that you have to be precise whether you're talking about radiance or reflected intensity. Okay, so anyway, there's more of this on the web book if you want to dig into it and think about it some more. So there's the proper statement. Each point reflects intensity in a cosine, but a Lambertian surface reflects radiance equally in all directions. So both of those statements are correct as long as you use the right measure of how you're talking about light. So then this Lambertian surface business, it turns out that the BRDF is just a reflectance rho divided by pi. And rho would be 0 for a black surface, there's no light being reflected. It would be 1 for a white surface that reflects all of the incident light. So if you have this BRDF here, and it's defined by this reflectivity rho, and we stick that into an equation for, let's say, computing R is equal to EU over ED, the radiance reflectance, well, okay, EU is reflected radiance times cosine integrated times solid angle integrated over all the reflected directions, and ED is L times cosine theta integrated over all the incident directions, just back to day 1 by the definition. But if we now take, remember we have this equation that says that the reflected light here, wherever it went, right here, we take that the reflected light is the incident times the BRDF, etc., integrated. And so we come back in here and say, okay, the reflected radiance here will be the incident times the BRDF integrated over all the incident directions, and then that reflected radiance is integrated over all the reflected directions. First thing to notice, if you have just in general any BRDF, this is as far as you can go. I mean, maybe you have some function you can plug it in, but in general, the irradiance reflectance of a surface depends both on the properties of the surface via the BRDF and on the incident light field. So there's not a unique measure of reflectance for a general surface. But if we have this BRDF of lambda, well, that's a nice simple little function. We plug in r over pi here, that doesn't depend on angles, so that can come out. And then we're left with an integral of Li cosine theta d omega there. We have the same thing in the denominator, so those two things cancel out. And then we're just left with an integral of cosine theta for the reflected angle integrated over all the reflected directions. And so that integrates to pi, and we end up with r just being equal to the reflectance. So for a Lambertian surface, the irradiance reflectance is just this reflectivity of the surface. So that's the nice result. In general, that's not true, but for Lambertian surfaces, it is. So the way hydrolite models bottom reflectances is it assumes, if you've got like a sand bottom, a seagrass bottom, whatever it is, it assumes the bottom is Lambertian. And then it says, okay, I have these measured bottom reflectances, which the way those are measured is, here's my sand bottom. So I take my little ED sensor and I put it right above the bottom, and that's getting the light coming down. And I measure ED and I turn it upside down, and ignoring shadowing effects at the moment, I then measure the EU that's coming up from the bottom, and then I get an R of the bottom. That's this ED measured right next to the bottom, or sorry, EU measured by the ED that's right next to the bottom. So that's how that actually, in principle, gets measured. And so then I have these measured spectra of different kinds of things. Very nice clean sand, all the way down to kelp and corals and seagrasses and so forth. So these were actually measured from 400 out to some of them 750, and some of them I think actually went to 800. So I take these spectra and I say, now if I assume the bottom is Lambertian, then I know the BRDF of the bottom. And so this gives me that reflectance rho that is used to define the BRDF. Now hydrolite doesn't require the bottom to be Lambertian, but people rarely have measured full BRDFs of real bottoms. Like Ken Voss had a paper where he measured the BRDF of some sand bottoms and so forth. And you know, it's reasonably close to Lambertian as long as you're looking more or less downward and the light's incident more or less onto it. But all surfaces, you know, a good approximation to like a Lambertian surface is some sort of cardboard like the gray cards we had. And you look at them this way, they're pretty good, but then when you look at them really at a grazing angle, they almost always start to look a little bit shiny, which tells you they're not really Lambertian, but they're good enough for most purposes. So that's how a Lambertian bottom is used in hydrolite to fix up the bottom boundary condition when you have finite depth. Okay, so the question now is, since BRDFs are absolutely fundamental to modeling surfaces, who knows more about BRDFs than anybody else in the whole world? And don't peek ahead. Any guesses? Who? Oh yeah, you got it. Okay, it's the movie people. So the way you generate some phony looking whatever is you make a little wire grid model, and then in each little point here, you pick an appropriate BRDF for skin, for clothes, for hair, whatever. You paste those BRDFs in here, little spot by little spot, and then you go do, guess what? A lot of Monte Carlo backward ray tracing. And you say, I'm going to look at this person from this direction, shoot my Monte Carlo rays out here, hits the chin, picks the BRDF, sends it off to this direction or sends it off to that direction. It goes up and says, oh, that's the sky radiance, or that's the radiance coming from the tree back there, does the backward Monte Carlo thing and says, if I'm looking at this point from this direction, this is what I would see. So that's the way that kind of stuff is done. Here's what's called a rendering of a sea surface, where they're increasing the waves on the surface from being kind of level to a little bit windier. And the sun's in the same place, and you can see the glitter pattern here, which once again is just a bunch of Monte Carlo ray tracings and a BRDF for the sea surface. And it can look amazingly realistic. So realistic, in fact. Well, here's another example. There was a movie when I first put this talk together, however many years ago. This movie, Monsters University, had just come out, so I was reading up on things. Well, they've got their little things here, monsters, whatever they are. Hollywood has had 20 years and unlimited funding to develop BRDFs for like dinosaur skin and people skin and monster fur and brick walls and, you know, whatever you want. Tree trunks, you name it. So they've got some enormous proprietary library with, who knows, 20,000 different kinds of BRDFs. And so then they make their little wire grid models, which they animate, you know, all very fancy. And then they paste in that, well, we need the BRDF for monster fur here, and we need the BRDF for green monster skin over here. Paste it all together, do a bunch of ray tracing, and you generate a frame of the movie. To make this one movie took over 100 million hours of computer time doing Monte Carlo ray tracing. And that was done with 24,000 cores running for 2 years at Pixar. I mean, it's just phenomenal level of computational power compared to what I have. You know, like, I think, man, I'm really hot. I did like this 2-week Monte Carlo simulation, and it takes days of computer time to generate one frame of a movie because the Monte Carlo calculations, you have to do so many rays traced to get things to look realistic. And so I was a little blown away, and there was actually online here somewhere a picture of this Pixar server farm. And this thing is like the size of the DMC, you know, and it's nothing but servers generating movies. It's just astounding. And then a couple of days ago in the New York Times, there was an article that says these influencers aren't flesh and blood, yet millions follow them. There are now people that are so realistic that the viewers watching commercials and so forth think these are real people. They're not. They're simply animations using Monte Carlo ray tracing and BRDFs. And they're so good, this says this advertising company commissioned the former fashion designer, somebody or another, to create a virtual army of digital models, including from left, that's Margot, Shudu, and Jur. And they're using these things in commercials, and people cannot be convinced that they're not real people. And there's another one of these who's a singer, and she has millions of people following her and downloading her songs, but it's all phony. She's just, you know, a Monte Carlo output. And people that download her songs say, no, she must be real. I've seen her on TV. And, okay, expect more of this the next election if you're in the U.S. Then there was an article I read, like, I don't know, maybe a year ago, that in Japan, they now have neural networks, and you can have your girlfriend or your boyfriend a neural network. And they interviewed this guy, and he's talking about, oh, he's got this girlfriend, and he sends her text messages, and, you know, they, I don't know, send each other birthday cards or whatever. And the interviewer said, well, you know, dude, this is not a real person. This is a computer program. Your girlfriend is a computer program. Do you not get that? And he says, well, it doesn't matter. She loves me. And I just kind of thought, you know, old people are always known for saying the world's going to pot, you know, and it's all over. Well, all I can say is if this guy doesn't know the difference in a real girlfriend and a neural network, the good news to come out of that is he's not going to reproduce himself. So Darwin may keep this under control with survival of the fittest. But anyway, that's what you can do if you're good with BRDFs. Okay, one little just bit of terminology here. When you read the reflectance literature, like at NIST or wherever, they will always, when they talk about a reflectance, they always stick on two adjectives. One tells you about the angular distribution of the light source, and one about the angular distribution of the reflected light. So the BRDF, it's a bidirectional reflectance because they're talking about one particular direction in and one particular direction out. That's what the BRDF tells you. Now the remote sensing reflectance is a hemispherical directional reflectance because it's taking all incident directions and talking about one direction coming out. And then the irradiance reflection is a hemispherical reflectance. It's taking all downward directions and then all upward reflected directions. So if, for example, there's a book in the back there by Hopke called Theory of Reflectance and Emittance Spectroscopy, when you read his book, he's always got, this is a hemispherical directional, and this is a directional hemispherical, and a bihemispherical, and blah, blah, blah. And I counted up one time, he defines 10 different reflectances and albedos in his book, none of which correspond to what oceanographers use. So be forewarned. He was interested in the moon and things like that. So anyway, it's a confusing mess, but that's the way it works. And so if you say something to some radiative transfer surface guy that, we measured RRS in the ocean, and he says, well, like, what kind of reflectance is that? Well, what he's looking for is that it's a hemispherical directional reflectance. And then he'll say, oh, I get it. And then the next question will be, well, how do you control the sky radiance distribution? Because people that work in the lab, they may want to have a uniform incident radiance onto their surface, and that removes a little bit of uncertainty. Well, we don't get to do that in the ocean. We have to take whatever the sky is today, unless it's May and June when it's cloudy, and then it's pretty much uniform. But anyway, that's a whole different can of worms, but just something to keep in mind is how the world works. So then a few words about how water surfaces reflect light. Okay, so presumably you've all somewhere in freshman physics seen the Snell's law business, that if you're going from air to water, the light, in this case we'll think of radiance, will come in, some will be reflected at the angle of incidence, and then some will be transmitted through by this little equation called Snell's law. Or if it's incident from the water side, it may be transmitted and reflected, or if it's coming in at too big of an angle, it's all internally reflected. So we've seen this law of reflection. Here's this Snell's law thing, and you can solve it for whatever you're interested in. And incidentally, the poor guy's name, he was Willebrod Snell van Rooyen. And so he's Dutch, he's around 1600. Well, in those days, you do all your science publications in Latin. So Snell became Snellius. That's his Latin name where he would publish his little equations here. So Snell became Snellius. Then later, they started going back to publishing in German and English and things. So they dropped the Latin part, and he ended up becoming Snell instead of going back to SNEL, which is what it should have been. So he's one of these guys that's doomed forever to have his name misspelled. Never mind the fact that Snell's law was discovered 600 years earlier by people sitting over in Baghdad and Tehran and places like that, but they made the mistake of publishing in Arabic instead of publishing in Latin, so they didn't get rediscovered for, another 800 years. Anyway, there is a movement, people like me and George Cadwar are now trying to publish it correctly or write it correctly, and then the reviewers always say, well, there's a typo in Snell here. No, it's actually, we're correct. Okay, so anyway, there's this little formula that says how is energy reflected by a surface or radiance reflected. That's Fresnel's law. And, you're given the incident and the final directions, and you can figure out what fraction of energy is going to be reflected. You've probably seen this equation around, and this is for unpolarized incident light being reflected into unpolarized. So if it's air incident water, it's roughly 2%, depending a little bit on the index of refraction, but it's roughly a couple of percent till you get out past 40 or 50 degrees, and then it rises quickly. If it's air incident, for nearly normal, it's the same, but then it rises really quickly till you get to this 48 degree or so angle of total internal reflection, and then the reflection's 100% from there on out. So you've seen those sorts of things. These equations go into computing how sea surfaces reflect light, and then when you have a windblown sea surface, so the way hydrolite works here, it's got this sea surface, and then the sun's up here. Let's say light comes in, it hits here. Well, here's your local normal that determines how the light is reflected and transmitted. And then if, let's say, the surface looks like this, then the light hits this point. Well, then here's the local normal that determines the reflection and the transmission. So each little calculation is just an application of Snell's law and the Fresnel law of reflectance. And then you do, guess what, a Monte Carlo simulation of the surface, trace a zillion rays, and you finally come up with the reflectance and transmission characteristics of the surface for a given wind speed, and so on. So that stuff you've seen, I think. Now we get to this little thing here, the n squared law for radiance. So here's a sea surface, and here's, let's say we're coming in this direction here, do the little Snell's law thing, and there's the direction that goes through into the light. Now if we come across in this direction, then this is going to be refracted into this direction here. Now, if we think of a bit of solid angle up here, defined by, here we're looking at a theta, and here's a little d theta, and then down here we're going to have some little bit of solid angle that's defined by this theta and a little d theta there. Now the catch, of course, is simply because of Snell's law, this bigger d theta ends up being a smaller d theta here. And then, of course, to get a real solid angle, you have to have like a d phi. And what it all boils down to is you can have a little big solid angle up here sending radiance down to the ocean, and all of that radiance goes into a little bit smaller solid angle underwater. And if you trace through the math here, which I'll just leave there for reference, but just applying Snell's law, then what you end up with is that this solid angle here is basically 1 over the index of refraction squared of the solid angle up there. So really, if you want to get the radiance in the water here, well, you take what you started with in the air, maybe 2% of that's reflected by the surface, so there's 97% or 98% gets through into the water. But now that same energy is going into a smaller solid angle. And so the radiance goes up by a factor of n squared because the solid angle went down by a factor of n squared. So in the water, that radiance would be like 1.76 times the radiance in air. And remember, it's the law of conservation of energy, not the law of conservation of radiance. And what's actually conserved for radiance as you go across a surface is what's called the reduced radiance. So get something you can see better there. So L in the air, over n squared in the air is equal to L in the water over n squared of the water. And then maybe there's some little transmission factor here that's what's reflected, but this is usually like 0.98 or so. So this is called the reduced radiance. It's radiance divided by the index of refraction of the medium. And that is actually then conserved going across the surface. So anyway, if you recall from the radiometry lecture, I know you've been waiting for 3 weeks now to find the answer here, where I showed you this plot of downwelling radiances, and the black curve is in the air, and then there's a couple of curves here just below the surface in the water and at 10 meters and then 50 and so on. And the question was, how can the radiance in the water be greater than the radiance in the air above the surface? And the answer is, it's the n squared law. So these guys are basically the one just below the surface here can be like 1 3/4 times the air value. And then eventually absorption starts killing it and the radiance decreases. But that's the answer to that. And I've had innumerable people send me emails saying, Curt, I ran hydrolyte, it's got a bigger radiance in the water than it does in the air. You know, it's obviously got a bug in it. And so I have to say, no, go learn some basic radiative transfer theory. Okay. All right. So then these fellows, Cox and Monk, that Jeremy Wardell mentioned, NASA uses the Cox-Monk treatment of the sea surface. So what's that all about? Well, back in '54, Chip Cox and Walter Monk at Scripps flew over the ocean in an airplane. They had a ship down here measuring wind speed. Here's an arrow, the wind's in this direction. And they literally just took photographs out the airplane window of the sun's glitter pattern. Then you can see they have taken this photograph. They've imposed a little coordinate system on it, all done by pen and ink, basically. And then by looking at the reflectance here, see if the sun's over here and I'm looking here and I see a bit of sun glint, I know I can calculate exactly how does that surface have to be tilted so that the sunlight will reflect towards me. If it's tilted this way, the sunlight will reflect off there and I won't see it. So they were able to literally sit down and analyze these pictures as a function of, you know, how far you are from the middle here and, you know, as a function of direction relative to the sun, and figure out what were the statistics of the sea surface for a given wind speed that would give me that glitter pattern. And the equations turned out to be really simple. The variance of the crosswind slopes is given by this little formula, and you plug in the wind speed in meters per second at, quote, anemometer height, which is usually taken to be 10 meters or 40 feet, or sorry, 12.5 meters or 40 feet. So they have an equation for the variance of the crosswind slopes and the variance of the upwind, downwind, or alongwind slopes, and then there's the total variance. So very simple little formulas that give you the variance. Now you can take these equations, plug in a wind speed, and doing a bunch of Monte Carlo stuff, you can generate random realizations of the sea surface and then shoot rays at it and eventually compute the reflectance and transmission properties of the sea surface. So that's what NASA does. They use these equations to get the statistical properties of the surface reflectance, which they then use to subtract out the sky reflectance when they're doing atmospheric correction. And Hydrolyte's original version, this is exactly what it uses. The next version also has a couple of other sea surface models, one of which is really, really fancy, and it doesn't make much difference at all. The catch, though, is when you're looking at this sea surface like Cox and Monk did, all you're really measuring is the slope of the surface. What angle was this wave facet tilted to give me my reflection? It doesn't give you any information about the elevation statistics, how big the waves are, just what the slopes are. So if you take the Cox-Monk equations and you generate, here's a little patch of sea surface, this little hexagon here. You generate a surface here. This has the right slope statistics of the real ocean sea surface, including everything from the biggest gravity waves down to the smallest little capillary waves. And so the optical properties here are pretty good, but it just doesn't look like a real sea surface. Here's the same thing generated, same wind speed and all of that, with a more realistic model of sea surfaces that reproduces both the slopes and the elevations. So you look at this, and of course it's expanded vertically, but this now looks more like a real sea surface. So when you're doing optics calculations, like how does this surface reflect and transmit light, this is fine. When you're actually standing out on the beach looking at the ocean and you say, wow, that's a really big wave, you're not looking at the slope of the surface, you're looking at the trough to crest distance of the wave. So visually, it's the elevation statistics that make the surface look right, but it's the slope statistics that give it the right optical properties for reflectance and transmittance. Emmanuel.
Yeah, but for wave focusing, you need the bottom one. You cannot get it from the top one.
Yeah. Now, funny story here. So there's this technique that generated this. It uses Fourier transforms and wave variance spectra and all of this. And I think maybe, I mentioned that here. You can do this right, you get the full-blown thing. You know, this has the same slope statistics as this. It just, in addition, has the correct elevation statistics. So I had this on my list since I was a postdoc with Preisendorfer, that one of these days I need to figure out how this Fourier transform business works. So a couple years ago, post-retirement, I literally spent like 4 or 5 months at the kitchen table trying to figure out this math, and it's enormously mess. And so there's a fellow named Jerry Tessendorf who's at Clemson, and he runs their, it's called something like their digital media lab, filmmaking, whatever. And he got an Academy Award for showing Hollywood how to generate sea surfaces. And like the first movie that used his technique was Waterworld. So in Waterworld, you'll see these pictures of the ocean here. They're all generated with this fancy Fourier transform technique. Well, I spend weeks like digging through these equations and programming them up, and I couldn't get them to work right, and they just weren't conserving energy. And so finally, I called Tessendorf up, and I know him from way back when, and I said, Jerry, I gotta tell you, like, your equations do not conserve energy. I just can't figure it out. And he says, oh yeah, I know, they don't conserve energy, but Hollywood doesn't care about conservation of energy. So he said, even if I give them a correct surface that might look like, you know, this, he said they have these things called graphics artists who will say, well, the surface doesn't look rough enough. Let's multiply it by a factor of 5, and we'll get this really ferocious looking sea surface for the movie. So he said it doesn't matter. If you give them the correct sea surface, they will screw it up making the movie, so no reason to worry about conservation of energy. Just give them something that looks sort of right, and they're going to squash it down or expand it or whatever. But he said, yeah, you're quite right. My equations don't conserve energy. Well, anyway, my equations do. I could not go to sleep knowing that I had violated a law of physics. It would be as bad as seeing lasers in space and having sound propagate through space. Anyway, so you can do this. It's a real mess. If you look on the web book, there's like 10 pages on the web book that work you through all of this math. And you can actually download the computer code to do all of this stuff. And I have a tutorial there that's like 80 pages or something to go through the math. You don't want to see it. But anyway, if you do that, then you can generate realistic looking sea surfaces. So here's a patch of ocean, 100 meters by 100 meters, and then sort of plus or minus 4 meters it looks like. So it's expanded on its axes just to see what it looks like. But so I'm doing the same thing Hollywood does. I'm screwing up the real world here. So here's 10 meters per second. It's a grid of 512 by 512 points and models for things called spreading functions and so forth. And here's the significant wave height in this particular image here is about 2.1 meters. Now the significant wave height is the average height of the highest 1/3 of the waves. So that's a common way people describe how rough the sea is. Here's the mean square slope in the along wind direction and in the crosswind direction, and the average angle of a wave facet, it's only like 7 or 8 degrees. But if you compare here, these numbers, here's the value from this simulation, and DFT stands for discrete Fourier transform. Here's the Cox-Monk formula, plug in the wind speed of 10, and you can see 0.031 versus 032, 021 versus 019, 052 versus 054. And that's just this one realization. So you can see it's giving the right numbers for everything. And if we can do this kind of stuff where here's one little wave facet, here's another one, light comes in, reflects off of one, goes over, hits another one, bounces off, and I have code that includes all the polarization and everything. It's a horrible mess, but it seems to work. So that's the way when I compute the polarized reflectance and transmission properties of a sea surface, I generate a realistic sea surface with the FFTs, then I do the ray tracing, Monte Carlo, including polarization, etc. And now, instead of having one little equation like that Fresnel reflectance, you now have a 4x4 matrix. It says, how does like vertical polarization reflect into horizontal and circular turn into unpolarized and so on. So it's basically a Mueller matrix for the sea surface, and there's 4 of them for downwelling reflected up, downwelling transmitted, upwelling transmitted through, and upwelling reflected back down. So instead of having one simple little formula, you now have these 4x4 matrices. And that's why you don't really want to look at this unless you're totally into polarization. Now, here's just a comparison of the irradiance reflectance of the surface using Cox-Monk with the open symbols and the full-blown Fourier transform stuff with the solid symbols. And here's like a wind speed of 15, wind speed of 5, 2. For wind speed of 0, they're identical. For 15, you can see as long as the sun angle, the incident sun angle, is out to like 50 degrees or so, there's almost no difference. Then there's a few percent difference if the sun's at like 80 degrees here, but having a few percent difference in irradiance reflectance is the least of your problems in oceanography. So it turns out in a sense, I was disappointed that I'd done all this work and it really doesn't matter. On the other hand, it's good because this means the Cox-Monk surface, which is really, really fast to run, is just about as good as the full-blown surface, which takes weeks to create these surfaces. So I'm off the hook with hydrolite there. In the next version, you can pick whichever one you want. Now, where it does matter, it doesn't matter on irradiance reflectances, but on the glitter pattern, when you're looking at, let's say, a low sun, and you're looking at that reflectance pattern, then you can see significant differences in the glitter pattern for the Cox-Monk versus the other surfaces. And I need to put in a figure on that, but I haven't done it. Okay, so here's,
Second.
yeah.
Question to the students. Which one do you think are the steepest waves in the ocean? The beach steep or the lakes? No, which are? What kind of waves are the steepest? Steepest, the biggest, smallest,
The greatest slopes, that's what you're saying.
right?
The biggest slopes.
Slopes. It's a calculated wave.
Yeah,
The smallest waves that we have.
yeah. Because in the real ocean, you may have these really long gravity waves like this, and this might be like 5 meters, but the slope isn't much. And then on top of that, you've got this really high frequency, but much steeper capillary waves. And those are the guys that really determine the optics for the reflectance part, and not those guys. Yeah. Yeah. Yeah.
It's in low wind states. You can see it's really confused.
Yeah, okay. And then you can also do time-dependent stuff with this Fourier transform business. So here's just a simulation, 20 seconds, kind of in real time, of, once again, 10 meter per second wind speed, and the wind's blowing this direction, the waves are propagating this direction, and it looks a little funny. I'm just kind of coloring the highest points white and the lowest points blue. And this looks a little bit lumpy, but there's this thing called the spreading function that you get to pick, and you can pick it to make kind of a lumpy looking ocean or kind of a lot of long linear waves, whatever you want to do, that's your call. And there's surprisingly little real measurements in the literature of these spreading functions and so forth, because to measure them, you have to make a 2D measurement of the wave state of the sea surface. Well, it's hard enough to put out some instrument and measure the slopes at one point here without having to measure the slope of, say, 100 by 100 meters, and you'd like to have it down to the centimeter scale. Just not going to happen. So people have very good data on the elevation statistics just going up and down, but not on this spreading function thing, which is kind of the 2D pattern of the waves. But anyway, you can see how the significant wave height's varying there, and these mean square slopes are pretty much what Cox Monks give you, and life is good. So anyway, that's kind of a solved problem. If you really need to generate time-dependent sea surfaces, you can do it. Yeah.
How does the time dependency go into the simulation?
Well,
Do you generate each frame separately?
yeah.
Based on the previous frame?
Really what's happening here is you're generating a sea surface here at time 0, and then you're propagating that surface where the propagation speed depends on the frequency. So the little capillary waves move fast and the big gravity waves move kind of slow. And you basically start out with that initial surface, and this is all over in Fourier space, and then you propagate the different frequencies at different speeds according to basic hydrodynamics equations for the speed of a wave, and you then get the next time step where the wave's going to be and the next one after that, and then away it goes. So
What do you do at the edges?
actually I've taken periodic boundary conditions, so this, and then when it runs off the end here, I'm just looping this and it comes back in here. So that's the normal sort of thing that's done. And of course, the calculations go up tremendously with the size and the smallest spatial scales and all of this. But enough said. Yeah. Okay, so here's the catch. Yeah, when you put an infinitely deep bottom in hydrolite, good question. So here's the depth, and you say run hydrolite down to 50 meters and make the water infinitely deep. So you're gonna, and so you save the output at 0, 10, 20, 30, 40, and 50. So it actually solves the radiative transfer equation down to those depths. And then what it does, there's a bunch of math that if you give me the IOPs of the water body, I can compute the BRDF of an infinitely deep layer with those properties. So if here's your IOP profile, whatever, hydrolite stops and says, okay, the IOPs at 50 meters are this, this, and this. I'm going to assume